All right. In this video, I'm going to talk about the law of universal gravitation, and I'm going to do some proofs. So the first one I'm going to do is the inverse square law. And basically what the inverse square law says is that the strength of something, right, it could be a force, it could be a gravity, varies as not as the inverse of the distance away from the source, but as the inverse of the square. So the relationship should be the strength of whatever that thing is. It could be the acceleration of gravity, it could be a force, is proportional not to the to the distance, but it's to the distance squared, inversely proportional, right? So let's see if we can use an example, an analogy, and see if I can convince you, right? So let's just imagine a little bit of light in space. Let's just say in this room, there's a dot of light right here, right where my finger is, right? Now, light has to spread in all directions, right? And just imagine with me that you have a bunch of spheres, right? Imaginary spheres surrounding this source, okay? So now what I'm going to draw here should be technically in 3D, right? So that's just a circle, but technically that's a sphere, right? And this source here, this light source, is right smack in the middle. If I want to find the strength, okay? So let's say this light source has an intensity I, or strength S, whatever you want to call it, right? If I go to the surface of that sphere, right, and I want to find the strength right in a unit area, meaning it could be a square inch, a square foot, a square yard, it doesn't matter, a unit area. Now, the area of a sphere is 4 pi r squared. So if I want to find how much of that, of I, is just covering that unit area, I think it would make sense to just say, well, it's I over the 4 pi r squared. So that's how much light per unit area is that area getting. Now, and this radius here is r. Now, if I go at twice the radius, okay? Now, this is 2r, okay, or 2d, whatever. Okay, so this I over 4 pi r squared is for that part. Now, if I take a similar area, which is right here, and this is in 3D, okay? A unit area, square inch or square centimeters, it doesn't matter. Now you can see that the intensity or of light, or the amount of light that this area is getting per unit area, it should be just I over 4 pi, the new radius, which is 2r squared. And you can see what I'm going with this. So it's I over 4 pi r squared. And the reason I wrote it like this, because I want to compare it to the previous intensity per surface area. And I see that a 1/2 square comes out here. Now, if I triple r, you see that it's 1/3 square. So here we say that the intensity of light but per unit area follows the inverse square law. Well, instead of thinking of light now, think of this red dot as a spot where there is some gravity, right? So think of it as like Earth, for instance, okay? Now, as you're going away from Earth, right? So let's say at the surface of the Earth, which means you are at a radius r from the center, the intensity of gravity is g, which is negative 9.8 or 10, okay? If you double the radius, in other words, if you go to an altitude that is twice the radius of the Earth, your g will be 1/4 of 10. All right, so now we're going to do some, we're going to do Newton's idea. So we're going to try to prove that really what's keeping the moon in orbit is just Earth's gravity. And we're going to do this 2 ways. The first way, I'm going to find the centripetal acceleration of the moon going around the Earth. Okay. Now this r here is not the radius of the of the moon is not the radius of the Earth, it's the radius of the orbit of the moon. So if Earth is here and the moon is up there, this R is right in here, following this path, in other words, right? Now I need to figure out what R is, and this number is given. So let me just look up some of these numbers here. Now this R is 3.8 times 10 to the 8 meters. This is in your data sheet in the back of the packet. And okay, now I need to find V. Now V, assuming that it goes around, the moon goes around in a circle, is 2 pi the radius of the orbit divided by the period, which is the time it takes the moon to go around the Earth once. Now this is going to be 2 pi 3.8 times 10 to the 8 over, now it takes 27.3 days for the moon to go around the Earth. So we have to change days to seconds. So 24 hours to a day and 3,600 seconds to an hour. And make sure you put this in parentheses when you divide. Now that should give us about 1,012.25 meters per second. So that's pretty fast. Now, if we do centripetal acceleration is equal to V squared over R, we should get 0.0027 meters per second squared. Now I'm going to try to do the acceleration, okay, that the moon feels, or the acceleration at the location of the moon, okay, because of Earth's presence. So at the surface of the Earth, which is 1 times the radius of the Earth. So when you are at the surface, the distance between you and the center of the Earth is 1 times the radius of the Earth. G is basically just 10 meters per second squared. Well, if you go at 2 times the radius of the Earth, which means 1 time the radius of the Earth above the surface. Now I just showed you earlier that G will follow the inverse square law, which is 1/4 of 10. Now I wrote it as 1 over 2 squared on purpose, right? So this is going to be 2.5 meters per second squared. At 3R, G will be 1 over 3 squared times 10, which is 1.11, just about. Okay. Well, the distance between the Earth and the location of the moon, okay, is a known number. That's about roughly between 59 and 60 times the radius of the Earth. Now, G is equal to 1 over 60 squared times 10. And that's equal to 0.0028 meters per second squared. Now, what does this prove? This proves that the centripetal acceleration of the moon going around the Earth is due to nothing other than gravity, because those two numbers match up. So now we just proved that the moon goes around the Earth because of Earth's gravity. Okay, there's no other way around that. Okay, so that's the conclusion. So maybe you want to write that in your notes. All right. Now I'm going to go up in the packet, and I'm going to so we pretty much just proved the first statement. Now I'm going to talk a little bit about let's see. Okay. It says the moon is constantly falling around the Earth. In other words, the moon, if it was up to the moon would just continue straight. But here it says the moon falls about 1.4 millimeters every second towards the Earth compared to if it were to go straight. Now, the Earth is here. The moon is up there. Okay? Okay. The moon wants to go along that path, but it drops, and it goes around in a circle. So in 1 second, okay, we can show that this number, this drop, is about 1.4 millimeters. Now we can do this 2 ways. And we can do this with geometry, or we can do it with trig, in other words, or we can do it with just the free fall stuff. Now think of the moon instead of going straight, it drops this way. That looks like it's a horizontal projectile. Okay. Now, for horizontal projectiles, if you remember, the delta y is 1/2 g times t squared. Now, the delta y is equal to, now the g at that location, which we just found earlier, is 1/2 0.0028. Now, we're trying to do this for 1 second. Okay, so if we do the math here, we get about 0.0014 meters. And that translates to about 1.4 millimeters. So that's a proof that the moon is actually not going straight, but it's dropping. And it's dropping by 1.4 millimeters. The other approach you can do, which might be a little trickier, is you can do a little bit of geometry. So the Earth is here. Okay. The moon is up there. So now the moon wants to continue straight, but it drops. Okay, so I'm going to make like a triangle here. So I'm trying to figure out what this distance is here, right? So if I work inside, I'm going to call this, this is Earth, and I'm just going to call this X, I guess. So if I work inside that triangle, M, X, and E, this is a right triangle, right? Right? So I can probably, I can do some geometry and figure out the inverse sine or cosine or tangent, whatever. And you can figure out, actually you can do Pythagorean theorem actually. Yeah, because this is the distance between the moon and the Earth. This is the distance between the moon and the Earth plus this X here, right? And I think we can, yeah, Pythagorean theorem, I don't think we'll cut it. And I think we can figure out this angle here actually, right? So that's the angle that you cover in 1 second when you're going around the moon. Now, in 27.3 days, okay, so the angle, you cover 360. In 27.3 days, which translates to this many seconds. Now, you want to find your angle, this angle here, that you cover in 1 second. So it's going to be an extremely small angle, right? So if you put that in here, you can do a little bit of trig and you can figure out the X. Okay? All right. And the reason this is a right triangle, because this is going, this is at the tangent kind of, right? And this is the radius, so they have to be perpendicular. But you don't have to do it this way. You can just do it the other way, thinking of the moon as being a horizontal projectile, and it falls. All right, the next thing I want to do is that I want to kind of like do a proof to the force of gravity. Now, if I have one mass here, and I have another mass here, okay? So if I have a mass and a mass, the force between them is 1F. Let's just say that's my standard. Now, if I double the mass here, if I make this one twice as heavy, and I leave this alone, it looks like I have 1F here and 1F here. So basically, I end up with 2F. Now, if I triple this side and I double this side, okay, now I can see there is 1, 2, 1, 2, and 1 and 2. So I end up with 6 forces. Here I end up with 2. Here I end up with 1. So now I can see that the force, it looks like it's proportional to the product of the masses. I hope you can see that. It's 1 times 1, 2 times 1, 3 times 2. So I can say that it's proportional to m1 times m2. Now, the force between these masses, the force of gravity, right, between these masses, follows the inverse square law also. So Fg is also proportional to 1 over the distance between the center of masses of these objects. So if I call that R. Okay, so if I combine these two ideas, okay, Fg proportional to the product of the masses divided by R squared. And this is just to compare. So for instance, if I have two objects, one has a small mass m, and the other one has, let's just say has m here too. And the distance between the centers is r. Let's just say my standard is that the force between those two is 1F, right? Now what will happen if I triple this mass, I double this mass, and I cut this radius in 4. Okay, let's see what happens. We can do this in steps. Now the fact that you're doubling the masses and the force is directly proportional to the product of the masses. So the fact that I double the masses should give me 6 times the force, right? But the radius got cut in 4. So there is an inverse relationship. So the fact that the radius is cut means the force has to increase. Now, it does not increase by 4. It increases by 4 squared, right? So then you can just do the math there. So it's 6 times 16, right? Which I think is 96. So the force here will be 96 times as much as it was before. Now, if you don't like to do it that way, you can just do this. Take those coefficients, 3 times 2 divided by 1/4 square, and you will get exactly the same thing. All right, I'm out. Peace.